I wanted to go over one of Affirm's blogs. What is Affirm? Affirm is essentially a buy now, pay later service offered in the US where you can buy a product at the given instant. However, you can pay for it in installments. And it's obviously become really popular with, especially within my generation, the younger generation, to buy a service at a certain instant and pay for it in installments or later because it gives the illusion that you're paying for things later and whatnot. But this blog is relatively old. It's from a year ago, but I still found it really interesting to read because it does the whole here is the problem statement, here's what we're looking for, and which this is why we picked one fundamental architecture over the other. And I had a great time reading it, and therefore I naturally wanted to talk about it. And essentially, without wasting any more time, here's the problem statement. So, the problem statement is essentially that whenever you go up to, let's say, a product like a company like Amazon or a website like Amazon.com or any one of the websites which allow you to check out, instead of just being able to check out, you also have an Affirm integration where you can buy now, pay later with Affirm. And one of the things that Affirm needs to make sure of on their end is that you are eligible for a buy now, pay later service. What does that mean? It means that Affirm needs to make sure that you aren't just someone who's had 15, 20 different missed payments. You're not someone, 15, 20 is an exaggerated number, but just generally you haven't had a lot of missed payments. You're not trying to commit fraud in any way. This isn't a bot and things like that. And for that, it needs to talk to a bunch of its different services. And all of this needs to happen while the customer actually, or the supposed legit customer, waits for a response on the UI. So what that essentially means is that I'm on, let's say this was Affirm's user interface, or let's say this was Amazon, and I clicked on checkout with Affirm. Affirm needs to perform checks for me specifically if I'm eligible for this buy now pay later service while I wait on the user interface. And the reason this is a slightly complicated problem is because Affirm needs to talk to multiple backend services of its. So it needs to talk to the identity service, to the underwriting service, and to the fraud service to make sure that I'm not someone just trying to commit fraud or I'm not a bot and things like that, and I'm actually eligible. And all of this technically needs to happen synchronously because I'm waiting for a response from the UI essentially. So that's the problem statement to solve for. And first, I will go over options, what Affirm's current architecture is, and and then eventually talk about what they ended up going with and why that actually makes sense from my understanding and my lens, basically. So the two options here are an event-driven architecture or a request-response architecture. What does that mean? So when Affirm's backend or HTTP API or whatever it is gets the request to say, hey, Anish is checking out, can you validate Anish is a valid customer and is not a bot and everything is okay, it needs to talk to these three different services. So a layer here receives, so let's say again here, the HTTP layer here receives the request saying Anish is trying to check out, please validate everything. So what I'll end up doing is that I will end up going over the current architecture and what the current architecture does. And I'll end up going through what the proposed architecture is and why they ended up going with that specific architecture and why that, in my very naive opinion, makes some sense and why different pieces fit together in what they're trying to achieve, essentially. So their current architecture essentially involves a client, which is me on the user interface trying to essentially check out with Affirm. We have an initial HTTP request that goes out saying, can you please verify that Anish is eligible to check out? We have that working. After that, what the checkout orchestration does on their backend is it makes an RPC call to the identity, underwriting, and fraud services, which are the three services that the checkout service or the HTTP service or the API, whatever it is, needs to talk to. And all of these essentially put or queue these tasks in a queue in RabbitMQ or whatever else queue. I think Affirm in this case specifically used RabbitMQ. And we have a worker fleet, which essentially is a bunch of workers which take each of these tasks and actually perform each of these tasks, aka perform fraud verification, perform identity verification, and things like that. Affirm hasn't talked about how all of this eventually lands back to the orchestration service and eventually gets responded back to the client. But my assumption is one of the sort of naive ways to do this is that once this worker fleet is done with a certain task, it queues it again in RabbitMQ, and we have a listener somewhere on the orchestration service or the HTTP API somewhere within there. And we have a continuous listener somewhere here, which eventually then is used to respond to back to the client. I'm not sure how that would completely work, but they've not talked about it in their blog. But my assumption is that we're requeuing the completed tasks which are eventually received by this checkout orchestration service, which is, I'm assuming, tightly coupled with the actual API itself, but not sure. But the fundamental idea here is that uh, identity underwriting and fraud services receive an RPC call, and all of this is queued in RabbitMQ, and eventually we get back to the orchestration service, and eventually we get back to the client. This architecture worked well for Affirm when the user base was not as big as it is today. And they ended up encountering a bunch of limitations on the worker fleet level, on even fundamentally with this queue system specifically. So some of their limitations, firstly, were latency and availability issues. Now, in this architecture specifically, in their worker fleets were written in Python, and the idea is that they were not able to completely utilize a system's concurrency, so to speak, because Python is single threaded and it doesn't allow you to run concurrent tasks. And to get over that limitation, they started using something called G event, I believe, which they've talked about here. Can quickly check. Yep, they started using G event. G event is, I think, from my limited understanding, a library which essentially allows you to be able to run concurrent tasks, not parallel, but concurrent tasks at the same time. So the worker fleet, from my understanding, ended up using G event. And one of the problems that they started encountering was that whenever they would use G event, they each specific task was actually called a greenlet. And the hard part about a greenlet is that whenever a certain greenlet would actually be extremely compute intensive, let's say within the worker fleet, one of the greenlets is extremely compute intensive and we have a bunch of concurrent tasks, suddenly the main thread itself would get blocked. And this means that it affects a bunch of the other operations that are occurring too. And suddenly we have a tight coupling of a bunch of different operations that are being performed on this worker fleet. And if one of them goes wrong, everything starts going wrong because a bunch of different tasks start going wrong and the main thread gets blocked, which creates the whole availability issues that Affirm has talked about, and latency just being sort of a byproduct of this, where because the main thread gets blocked, suddenly a bunch of different tasks start having latency issues. A bunch of different tasks respond much later to the checkout orchestration service, even if it is, let's say, a failure message saying that Affirm wasn't able to process the specific request or whatever it is. So that is one of the bigger limitations that they've talked about. So again, as written here in the second and third point, they used G event for concurrency, which is a library that allows you to do so, and a greenlet, which is meant to be a specific task here that is done by the workers. Whenever it would be extremely compute intensive, it would cause availability issues, and the main thread itself would get blocked, which causes issues. So and this happened as the user base increased and as the number of tasks that these workers were performing continuously increased, and their workers were horizontally scaling to a number of workers, fleet of workers doing a bunch of these tasks that they received from RabbitMQ, which was the queuing mechanism that they ended up using. And also, the other thing that they've talked about in the blog is that it was extremely hard to drill down specifically which tasks were consuming a lot of memory, because or which tasks were CPU intensive, because generally it ended up, from what Affirm's talked about, it ended up being a limitation with using greenlets, where it was really hard to drill down metrics as to which specific task out of all the concurrent tasks running was actually the one that was CPU intensive. And I believe they even have another blog about it where they've talked about um, essentially profiling G events in Python and essentially drilling down metrics, creating dashboards out of it, and how they weren't really able to specifically understand why certain tasks were, which tasks were computationally expensive within a set of tasks that were concurrently running. And I think they've little bit talked, yeah, they've talked about dashboards here essentially. And I think this looks like Grafana. I'm not sure, but essentially, yeah. So the long story short is that they encountered a bunch of limitations, and this prompted the re-architecture or the rethinking of their fundamental architecture, basically. So now to go over a firm's requirements. So because they were trying to rethink the entire architecture as that user base was increasing, the fundamental requirements were one, low latency, two, timing out user requests. Low latency is obviously obvious. You want to make sure that when a user is sitting on their user interface and actually waiting for a firm to confirm if they're okay to use the buy now pay later service, ideally it is as low latency as possible when talking to each of these different services. We also have timing out user requests. So currently, and we will actually come to this when we try and evaluate an event driven architecture again, but one of the things is that they really want is to be able to time out user requests. So an example or a parallel to this is that whenever you make an HTTP request to, let's say, a server or to an API, or whether it's an external third-party API or your own API, you generally have a timeout for how long that request gets tried for, and eventually that request would time out. So, for example, if I'm trying to get, let's say, data from S3 and I'm using the AWS SDK, right? I send out an HTTP request to the AWS underlying API, let's say from their SDK, to get a bunch of S3 objects. If that request doesn't get fulfilled in about 30 seconds, let's say 30 is the general default timeout, it could be anything, it could be 60, 120, whatever it is, eventually the request times out. And eventually you get back a response from the AWS API saying this request is timed out, please try again, or whatever else it is, or if there's a better error message available. So Affirm wants a way to be able to do exactly that, where if I go on to checking out with Affirm with their integration, and if something has gone wrong or if something isn't working, they time out in, let's say, 60 or 120 seconds or 30 seconds or whatever else it is. And the user should be able to see that the request is timed out, please retry again, or again if there's a better error message available. So the second thing is being able to do that. The third thing is being able to determine the request status. That means that when I send out a checkout request, ideally the backend itself, or let's say when the UI requests for it, let's say on a polling interval every, let's say, n seconds, I should be able to tell what is the status of a current request, aka if it is currently in processing, if it has failed, if it is completed, or if it's in completion, the number of seconds it's taken, essentially metrics associated with what is happening with a specific request of a specific user. So let's say when I send out a request from my browser to Affirm's API saying, please orchestrate checkout, or please check if I'm eligible, and it's talking to these three services, ideally I should be able to have granular metrics or statuses saying, okay, currently the request is in process, currently the request is failed, and if the request is failed, then we just send back a response back to the UI saying the request is failed, please try again, whatever else it is. So being able to determine request status, and thirdly, process level tracing capabilities. So as Affirm talked about this earlier in their previous architecture, they were using G events, and let's say if a certain greenlet ended up being compute intensive, it would essentially mean that it blocks the main thread, and it was really hard to drill down which specific process was actually computationally expensive when using G events and greenlets. And one of the requirements is being able to have tracing down to per process. And this gives visibility into what's taking time, what's not taking time, things like that. And also fundamentally, just moving away from this main thread being blocked when concurrent tasks are being performed, and one of them ends up being computationally expensive, basically. So one of the options is an event-driven architecture, which means that a client, which is the UI, makes a request, an HTTP request to their API, and we then emit, let's say, a message into a certain Kafka topic, which is consumed by the identity, underwriting, and fraud services. Each of these do their thing, and eventually we send back a message to using Kafka to the checkout orchestration service, or the one that actually, the service that actually orchestrates sending out each of these tasks, and eventually we respond back from, which I'm assuming these two are tightly coupled, and then we eventually respond back from the HTTP API back to the client. And in this way, there are a couple of things happening. Firstly, this is extremely decoupled in the sense that the checkout orchestration service is just responsible for sending out request events to each of these services, and Kafka is the one that's doing the heavy loading of consuming, and eventually each of these services do their thing, and Kafka also sends back an event to the checkout orchestration service, which is used to respond back to the client. So some of the limitations of this specific architecture are based on our requirements. Firstly, there is still no way to determine the current request status. What does that mean? It means that one of the problems that we wanted to solve for, or one of the requirements that we wanted to solve for, is we wanted to know what is the current status of a specific request, which means that if the checkout orchestration service sends out a request for Anisha's request to actually verify if I'm okay to do the buy now pay later service to the identity, underwriting, and fraud services, there is no direct underlying way to determine what the request status is, simply because we're just sending out the message, we're sending out to the identity service, underwriting service, fraud services, which are doing a bunch of their things. However, there is no real way or no underlying way when using message queues to actually determine where the request currently lies across each of these services. And there is one way where we can sort of solve this by having another new service, which is the observer service, which also actually receives events from these queues. So we'll have two different consumers for these Kafka topics essentially. And that helps, that observer service is receiving all of these events, which would sort of help us form an idea of where the request actually is. But one, it requires building out an entirely new service which is responsible for just observing and tracing where the request actually lies in the current flow. And the other problem, which makes this even trickier, is that, let's say, suddenly on Christmas there are, or some festival, let's say Diwali, an Indian festival, a lot of requests start piling up within the queue. What does that mean? It means that, let's say, there's a lot of traffic on the checkout orchestration service because it's Diwali, and continuously Kafka is receiving a bunch of events which are being consumed by the identity service, and at one point Kafka is starting to get overwhelmed. One of the classic ways of dealing with this is that you throttle the producer itself, which means that we stop the producer from emitting these many events so that the consumption of these events becomes slower, and the consumer itself doesn't get overwhelmed. And this might be a little bit of an issue because this means that we're not able to get the true status of a request by the observer service, because the observer service fundamentally depends on actually receiving these events all on time. However, in this case, it actually wouldn't, because it's actually stuck in flight in between the queue, which is a problem and it needs to be solved for. And that makes it extremely tricky. So statuses may be stale, essentially, which means that we're getting the status of a request much later, which may not be ideal, right? And there is no real deterministic nature of if the identity service and the underlying observer service, both of them receive the event at the exact same time, because a certain consumer within, let's say, a consumer group could theoretically receive it faster than the other consumer who is also consuming for that event, and there isn't a direct deterministic way. But the underlying problem is also that there needs to be a maintained observer service, which is observing for events that are coming out of the queue. And again, this whole buffering problem, where if the queue starts getting overwhelmed, it gets even harder to trace the certain status of a request, even if it's in the queue. So that's one of the harder parts. And again, determining request status becomes the hard part here, the big limitation. And that also contributes to the whole timing out thing, because we now at this point we don't even, if even if there is a way to time out the request, we actually don't even know how why we're timing out the request, because it may just be stuck in the queue and eventually the identity service receives it. And again, there's a lot of different moving parts here. And the fundamental reason there's a lot of these different moving parts here is because we've decoupled everything, which means that when the HTTP API actually receives the request for the checkout experience, the checkout orchestration service just sends a bunch of messages into Kafka topics, and each of these are just extremely decoupled and doing their own thing and eventually publishing a message back into Kafka on a topic, which is eventually received by checkout orchestration and then responds. But the hard part is that we've decoupled everything, which is generally a good practice, that you're decoupling different services, you're trying to remove the coupling between two different services which are doing two different things, single responsibility principle. But we here in this use case, we actually want the coupling, because we want everything to be tightly coupled within this whole request flow, so that we can time out the request, we can determine where the request status is, and we know what the request status is. So this is essentially the final architecture. Their final architecture fundamentally is that the user interface sends out a checkout orchestration request, and they are now Affirm now moved to a request response model, where we send out an RPC call, which is basically the underlying mode of an RPC is the request response model, and it can happen over HTTP or not over HTTP. It can literally be raw TCP also if needed, but I would assume it's HTTP. And essentially, we make a bunch of RPC calls to each of these services, and we eventually just wait for a response, and we sort of aggregate the response and send it back to via the HTTP API over to the client. And this is phenomenal, and so much better, because if we now look back at the requirements list, one, it's low latency, because theoretically, with queues, the whole point of also a queue, not the whole point, but one of the points of a queue is that you avoid the network HTTP overhead. However, if the queue starts piling up, or if the consumer service is slow, the production of messages also becomes slow. So essentially, everything becomes slower. And this is actually not great on, let's say, Christmas Day, because suddenly what was meant to decrease latency because there is no network overhead actually increases latency when there's more traffic. So that's not great. And the RPCs actually sort of mandate that even if there is a little bit of network overhead, if this request is going over HTTP, it's still better, because we have more tracing as to where the request is, which request is taking time. So for example, we're just sending out, think of it as just an HTTP call to each of these services. We can time out each of these requests, and because let's say it's over HTTP, we have very process level tracing capability. So we can track how much time, what latency, and how much CPU intensive each of these processes are as they're receiving requests. And it's also a lot easier to determine request status, because now it's just simple RPC calls, and we have none of the messages stuck in a queue, because let's say the consumer service is getting overwhelmed, or the queue service itself is getting overwhelmed. So this becomes a lot easier. And also, the good thing that Affirm also talks about is, let's say if when we respond back via these RPCs to the checkout orchestration service, let's say we actually need to do something asynchronous too. So for example, let's say send the user an email about, oh, you are now verified with Affirm to checkout. That's just an example. We can also do it by sending, but once we receive the RPC response, we can just fire up an event, let's say in Kafka, RabbitMQ, NATS, or whatever else it is, and that can asynchronously have a consumer which sends an email to the user. And this is a great blog, because generally, whenever you think of one service sending out requests to multiple services, the first instinct is let's use a queue, because it decouples everything, and it makes sort of the whole problem around, if the consumer is getting overwhelmed, then you can slow down the producer, and a queue really allows you to manage all of this together. But this is one of the interesting use cases where you don't need the decoupling despite sending out requests to a bunch of these different services. And what you actually ended up needing is a whole request response model, because you need to be able to trace which specific process in this specific process of checkout is actually taking a lot of time, is actually taking a lot, is CPU intensive, memory intensive, and you can create Grafana dashboards out of this, run Prometheus queries, um, and things like that. So that should be it for me, and I will figure out what to talk about in the next one. And I know what I'll talk about. I will talk about Kubernetes operators. So that should be it for me, and I will be back in the next one.